Topic number 1. We said that we have one s orbital and one s orbital. They can combine with the plus sign, minus sign, giving you the bonding bond or anti-bonding orbitals. Now what happens if you have 3 of them? Well, then we said that if you have 3 of them, then probably if they have starting energy, one of them would be bonding, one of them anti-bonding, and one of them would be no bonding. What happens if you have 4 of them? Probably in the case of 4 of them, the situation will look like that. Let's only from now on analyze the even number. So 6, the situation would look like that. 1, 2, 3, 4, 5, 6. If you go even farther, let's say 100, and this is the 100 of them here. $50 of them will go up, and 50 of them will go down. Now what happens if instead of 100 I put here 10,000? Nothing except that virtually you get here a continuous line. What happens if you go to infinity, like it is in crystal? The difference between 2 lines here goes to 0. So you really have a continuous band, which is called valence band. And this one is called conduction band. Now, if each of these orbitals has only one single electron, and so on here, times 1 electron, then these levels, each of them, will be doubly occupied. And this one will be 0 times occupied. It means this one is completely full and this one is completely empty. But it doesn't have to be this situation. Maybe it doesn't have 1 electron, or maybe there are not only s orbitals making these bands. You can imagine the following situations. First, let's just analyze what is the difference. Let's call it delta E. When delta E is equal 0, we call this crystal metal. When delta E is large, we call this crystal insulator. And when delta E is small, we call this crystal semiconductor. And this delta E usually is called Fermi gap. Now, few situations can happen. it can happen that in these fully occupied orbitals, some of them on the top are empty. Not many, just a few. Okay? This is situation number one. If this is the situation like that, then we call this system first if delta E small. So first we know it will be a semiconductor, and second, if some orbitals in valence band are empty, we call this type p-type semiconductor. Now imagine the other situation. When you have again valence band, conduction band. This one is again fully occupied. And now, instead of having here a few empty orbitals, you have here a few occupied ones, but not many, just a few. Well, to be honest, when I say few, I probably means billions of them, but the real meaning of few is that the energy is not too high. Okay, just very close to the lower limit of them. This type is called N-type semiconductor. And this is the simple picture. You will learn the difficult picture in the solid state physics class when you learn about the Brillouin zone and the momentum space, and you will be plotting the orbitals in the momentum space. And then you will really understand the meaning of metal and insulator. We just cannot do it. It's too complicated for now. But everything what I want you to remember is on the blackboard about crystals and the electronic structure of crystals. Good. So this is one topic we wanted to discuss today. Another topic I want to discuss today is dipole moment. And what you have to learn in this class is which molecules have dipole moment and which molecules do not have dipole moments. In fact, it will turn out to be very easy, and you will see that the important thing that defines the dipole moment is the symmetry. Inversion symmetry. And I need blackboard, so I remove this part. And let us write a few molecules. First of them may be water. H, O, H. Next one will be CO2. Next one may be, give me some ideas. Whatever. Thank you. By the way, the other one was wrong? The answer is no. It just has higher energy. So let's continue. Maybe NH3. Something more. N2. Something more. Good. Maybe enough 5. So now, for all of these molecules, I'm finding the center of mass. Okay? It means if I rotate this molecule, whatever direction the molecule rotates about 1 point, the center of mass. And for oxygen, you have mass 1, and mass 16. So probably the center of mass will be very close to oxygen. And now, since this mass and this mass are symmetric with respect to this plane, then the center of mass must be on this line, in fact, somewhere here. Now, on this line will be probably closer to oxygen. So center of mass of this molecule must be somewhere here. For this molecule, it's simple. Center of mass is here. For this molecule, again, similar situation to water. The hydrogen are 120, 120, 120. So the center of mass will be somewhere on this line and probably closer to the nitrogen instead of the hydrogen. So let's say here. In nitrogen, again, it's easy, center of mass. And here is again easy. Okay, I defined the center of mass. So the yellow dot is equal if somebody likes mathematical equations, then the center of mass is given as once again I equal 1 to the number of atoms, and you have the position of the atom I multiplied by the mass of the atom I divided by the so just simple mathematical definition, but we just know more or less how to find it. So we have for all these molecule center of mass. Now we define the inversion operator or inversion operator. And I defined the inversion operator acting on a point P gives me inversion operator acting on the coordinates xp, yp, and zp gives me the point with coordinate minus xp, minus yp, minus zp. How does it look geometrically? Very simple. If I make a system of coordinates, and take a point P with the coordinates xp, yp, and zp, I can write down that these coordinates this is the z, x, y, and x. Now what the inversion operator does, the inversion operator takes the point, brings it to 0, then continues on this line at the same distance like here, and brings the point here. Here is the point inversion operated on P with the coordinates minus xp, minus yp, minus zp. Good. That's why we needed the center of mass. The center of mass is the 0, 0, 0 point for us. So now we are moving each atom to the other side of center of mass. So oxygen, being here, goes on the other side of center of mass, probably around here. That's the new position of oxygen after inversion. The hydrogen goes to this point and then to other side. Now it's here. This one goes to the other side, somewhere here. We get a new molecule that looks like that. Now we do the same for this one. This oxygen comes to the other side and becomes this oxygen. This oxygen goes here and becomes this oxygen. Carbon stays in the same place. Nitrogen comes here. And the other three hydrogens come here, here, and here. Once again, nitrogen comes here, and the other one comes here, here, and there. For nitrogen, you see that nothing interesting happens. And for, this is interesting case, one hydrogen comes here, this one comes here, carbon stays in the place. And what else? This one is here, this one is here, and one is there. Good. Now we see that this molecule looks exactly the same like it looked before. This one has no dipole moment. This one looks exactly the same it looked before. No dipole moment. Okay? So this is one way of finding if a molecule has or it doesn't have a dipole moment. This molecule and this molecule and this molecule may have dipole moment. Turns out that this one has, and this one doesn't have. Strong one. Okay, let's continue. Okay, so the first way of checking if the molecule has a dipole moment is checking if the inversion operator makes the molecule looking exactly the same after inversion. So now we can apply this knowledge to some real situations, and this real situation could be, for example, this. Later we will discuss why this molecule doesn't have dipole moment. But let's first apply the knowledge we have to the situation like that. Let's consider all structures that look like that. And now here can be hydrogen or chlorine. Here can be hydrogen or chlorine. Again, hydrogen or chlorine, hydrogen or chlorine. Let us write down all possible structures that can come out of that. And we'll analyze if they have dipole moments or not. So the simplest one is with hydrogens only. Next one would be a structure with one chlorine. You see that putting the chlorine here or here or here doesn't make any difference. It's the same structure. We can always rotate and get back. Now the structures with two chlorines. One of them would be chlorine, chlorine, hydrogen, hydrogen. Next one. Chlorine, chlorine, hydrogen, hydrogen. Chlorine, chlorine, hydrogen, and hydrogen. This is, I guess, all the possibilities we can have with three. And then with two. With three chlorines, there is only one possibility. And then only one possibility with four chlorines. Now, fast look into this structure shows that this molecule has a center of inversion because this chlorine goes here, this chlorine comes here, this one goes here, and carbons are changing places. Similar, this one has a center of inversion for the same reason. The hydrogen goes here, they change, these two change, and these two change. They look the same. Next, which other structure here have? This one maybe, but this one hydrogen and chlorine change places. No, no, no. Yes, this chlorine comes to this chlorine, this hydrogen comes here, and carbon change places. So this structure has dipole moments, no dipole moments. So for here we say dipole moment equals 0. For here say dipole moment equals 0. And for here dipole moment equals 0. Good. What about other ones? All of the others one molecules, this, and this, they have dipole moments. Now, this inversion symmetry doesn't tell us how the dipole moments look like. It's a vector there, it's a vector here, or it's a vector there. We don't know. Let us try to find the dipole moment based on the molecular information. So I keep this one here. We know that these three structures, they don't have dipole moments, so they are not very interesting for us anymore. But for that one that have dipole moment, let us try to find where the dipole moment goes. Good. To start this, we take atom A and atom B molecule. Now, everything what I know is that the electronegativity of atom A is larger than the electronegativity than atom B. It means that the electronic cloud is not symmetric as I expect, but since this one has larger electronegativity, it wants to pull the electrons more. The electronic cloud looks rather something like that. Since more electrons is closer to the atom A has a small negative charge, and atom B has a small positive charge. Okay? So now you define a momentum, the dipole moment, from plus to minus induced charge. So what it means? It means that this molecule has a dipole moment starting in the plus center and going to the minus center. So the dipole moment looks like that in this molecule. If somebody doesn't remember what it was the dipole moment, the definition of dipole moment goes like that. Is the delta R minus, where this is a vector defining the place where the positive charge is, and this is the vector defining the place where the negative charge is. Good. So now we see that virtually every bond is polarized. It means that if I write a molecule, for example NH3, then every bond has a small dipole moment. For example, pointing from plus charge to the negative charge. So every bond has a small dipole moment. Now, if you look at these dipole moments from the top, from this direction, the dipole moments would look something like that. Of course, every bond has the same dipole moment, just the direction is different. So now they have two components. One component is in the plane, other component is here, as every vector. You see that the components that I wrote here, this one and this one, they will completely cancel. This plus this is 0. But these components, they will add together. So finally, the molecular dipole is pointing this direction. Similarly for water. For water it's maybe even easier to understand because this is planar. I have one hydrogen, another hydrogen, And every bond has a small dipole. Hydrogen is less electronegative than oxygen. Oxygen is attracting electrons more. So we see that the dipole bond, the dipole on the bond will be here. Now this dipole will be here. The total molecular dipole will be the sum of these two. And if you add this plus this, you get a vector that looks like that. So the vector, the dipole of this molecule is pointing in this direction. Good. Let's go further. Now we are ready to analyze these three things, but to understand how big are the dipoles, we probably have to open the book in chapter 2 and check what are the electronegativities. And that would be page 73 and figure 212. Page 73 and figure 212, and we find that the electronegativity of carbon is 2.6. Electronegativity of hydrogen is 2.2. And the electronegativity of chlorine is 3.6. 3.2. So now we are ready to analyze how are the bond dipoles. Clearly, between carbon and carbon, they have the same electronegativity, no dipole on the bond. Similar, no dipole, no dipole, no dipole. What about hydrogen and carbon? Carbon is higher electronegativity, so there would be a Now, chlorine has higher electronegativity than carbon. And you see the difference here was 0.4. The difference between these two is 0.6. So the dipole would be larger, somewhat larger. So we see that from carbon to chlorine, we are drawing longer arrow. Good, everything. Let's go further with this. You see that this arrow and this arrow are exactly the same direction, so they will cancel. Now this one don't cancel because they have different value, 0.4, 0.6. Now here nothing cancels, here these two cancel. Good. That's nice, because in this way we found the total dipole of each moment, of each molecule. You see that for this one is showing here, one is showing there, so the total dipole of the molecule will be somewhere there. In this case, this part and this part, these components cancel, these components add. The same happens here. These components cancel, this component add. So final dipole of this molecule will be something like that. In this case, the final dipole of this molecule, for the same reason, will be something like this. And in this case, the final dipole of the molecule will be something like this. It's just adding arrows together. Not very complicated. Good. Now is the difficult case that we had in the first moment. we found that this molecule doesn't have the center of inversion, but I said it doesn't have dipole moment either. How to prove it? Well, if you think about moment longer about these arrows, then you see that all of them have small dipoles in this direction. Now, if you think about all these arrows add together, you clearly see that the summation is 0. Because if you look from this direction, then this, and this will give you some vector in this direction. And these three components in this, 1, 2, 3, will give exactly the same sign like these components. How I do know that they will give me exactly the same sign? So let's assume for a moment they don't give you exactly the same sign. So you get some vector, let's say like that. But now I tell you to close your eyes, and I'm writing this molecule once again. Like that. When the hydrogen 1 is not anymore here, but I rotated everything here. If I rotate it, then something what was hydrogen, okay, sorry, I wrote it in the wrong way. Yes. So hydrogen 1 is not anymore here, I rotated it now here. So this rotation in this direction brings me what? That was the rotation on this axis. H1 came here, H2 went to the back, and H3 came here, H3. And H4 didn't move. So that was the rotation on the axis by the angle 120 degrees. But if this is the true, then also my dipole moment rotated. So the dipole moment doesn't show anymore here, but now it shows in this direction. But the molecule looks exactly the same. It means the dipole moment for this molecule and the dipole moment for this molecule must be the same because the molecule is the same molecule. It looks exactly the same, no difference. It means if this vector and this vector must be equal, the only possibility is that both of them are 0. So in this case, for this molecule, not the inversion symmetry makes the dipole moment 0, but the rotational symmetry makes the dipole exactly 0. But the idea is more or less the same. So there are two ways of analyzing if the molecule has dipole or not. First one is analyzing the bond dipoles and adding them together. Second one is that you just look at all symmetry operation and check if this operation of symmetry gives you 0 or not. Like in this case, they gave you 0. Good. Now, there is one danger about using bond dipoles. For example, if you take a molecule carbon and oxygen, they have different electronegativity of around 0.8, and you see that each of these bonds has a dipole. So the bond dipoles exist, but they are exactly opposite direction and they cancel. So the dipole of the molecule is 0, which we can see clearly immediately from the inversion symmetry. So I think it's good to know both ways. The dipole on the bonds, adding them together, and the inversional symmetry.